Hello everyone and welcome back to the series on heaps. Today we'll be discussing top k frequent elements problem, and this is one of the most standard problem when it comes to heap and one of the most obvious application of heaps. And this problem actually you might find in some of your interviews, the online tests or the on-site interviews. So I thought that it might be good to discuss this problem. So let's get started. So the problem statement says that given an integer array nums and an integer k, return the k most frequent elements. You may return the answer in any order. So the problem seems very simple in first glance. So what we need to do is that we need to calculate the frequency of each element in the array and then return the topmost k element. So in this particular example which is given to us, so we have 1, 1, 2, 2, 3. So the frequency of 1 is 3, frequency of 2 is 2, and frequency of 3 is 1. So the topmost elements or the two topmost elements with the highest frequency are obviously 1 with frequency 3 and 2 with frequency 2. So what could be one of the nice solutions for this problem? So it could be that we create a vector with the element and their frequency and then sort the vector and then return the k last k cells of that vector. So what we can do is that, like, we can create a vector. Here we have three distinct elements, so we'll create a vector in which we will store the pair of the frequency and element itself. So it'll be 3 comma 1, then 2 comma 2, and the next will be 1 comma 3, and then we'll sort this vector. And when we sort this vector, obviously first it will get sorted based on their frequency. So after sorting, the vector would look something like this: 1 comma 3, 2 comma 2, and 3 comma 1. So I'm basically storing frequency comma element. So we return the last k cells, or in this case we'll return the last two cells, which is again 2 and 1. So what is the time complexity of this solution? Basically we have to parse the entire given array, so that will take big O of n time, and then we have to sort our resulting array, so that will take big O of n log n time, and then we need to return the k last cells, but that is just a linear parsing of the arrays and the time complexity will be big O of k. So the time complexity for this solution turns out to be n log n. Now let's come to our second solution. So since we are discussing this question in the series on heaps, so you might have guessed that this can be solved using heaps as well. But how can it be solved using heaps? So we know that heap kind of maintains the ordering between the elements in the sense that the greatest element of the collection is always at the root, and then we can remove whenever we call extract or delete operation on our heap, it always returns the greatest element. So what if we make a heap of these elements and then remove k elements by calling extract or delete method k times? So every time we'll get the greatest element in the remaining heap, and that's how we'll get the k topmost frequent elements. So let's try that out as well. So each node in the heap will again store a pair, and the pair would be frequency comma the element itself. Now the three different nodes that I have are 3 comma 1, 2 comma 2 again, and 1 comma 3. Now if I make a max heap, let's try to visualize how the max heap would look for this particular array. So one thing that we need to keep in mind is that whenever we are doing comparison between two pairs, the comparison will first happen on the first element. So if I'm comparing 3 comma 1 and 2 comma 2, the comparison will happen between the first elements of the pair, and since 3 is greater than 2, so I will get that 3 comma 1 is actually greater than 2 comma 2. But in the case where the first element would have been same, in the case of a conflict, so if I'm comparing two pairs, say 3 comma 2 and 3 comma 1, when the first elements are same, then the comparison goes on the second value. So in this case 3 comma 2 would be bigger. So we need to keep this in mind, because in heap our complete logic depends on the comparison between values. So if I insert these elements into the heap, let's see how the heap will look. So first 3 comma 1 will go into our heap, so it will become this node. Then 2 comma 2 is going to go into our heap, so it will be inserted at the last node, and then up heapify will be called on this particular node. Since 2 is smaller than 3, so obviously this node is at its correct position, so there will not be any swap between the parent or this node. And then we'll move to our next element, which is 1 comma 3. 1 comma 3 will be added as the last node, and then up heapify will be called on this node. But again 3 is greater than 1, so this node is at its correct position and no swapping will happen between the last node and the parent. So this is how our heap would look like. Now what I need to do is I need to call the extract method k times, and if I call the extract method k times, then first 3 comma 1 will be extracted and then 2 comma 2 will be extracted, because always the largest remaining element from the heap will be extracted. So let's see what would be the time complexity for this solution. As we discussed that to make a heap of size n, it is going to take big O of n time. And then I'm going to call extract method k times, and each time the extract method, since the size of the heap is going to be n, so each time the extract method is going to take log n of time. So we already know that the time complexity for the delete or extract method is log n. So the final time complexity, that is going to be big O of n plus big O of k log n. So I've actually not removed this term from the time complexity, because in case where k is very smaller than n, then the overall time complexity is going to be big O of n. In case where the order of k and n is almost similar, the time complexity is going to be big O of k log n, and obviously k cannot be greater than n, so this case is not possible. Now let's try to see how can we further optimize this particular approach. So if we try to think about our previous approach, in that what we were doing, we were adding all the distinct elements to our heap. Now let's think about it. If there are n distinct elements and I just need to get the k topmost or the k most frequent elements, do I actually need to store the frequency for all the elements in the heap? Why can't I just maintain a heap which holds the k most frequent elements till now? So I do not allow the size of my heap to go beyond k, because towards the at the end I only need k most frequent elements. I don't care about all the n minus k elements which are there. So why do I need to actually store all the n elements into my heap? So what is the harm of storing all the n elements into the heap? In when I am extracting elements from the heap, then the heap will be bigger, and if the heap is bigger, the extract or delete method is going to take more time. If I keep the size of my heap smaller or just equal to the exact size I need towards the end, then extract and delete method will actually become much more efficient. So let's try to understand this approach a little better again with the same example, or maybe let's try to take a different example, a bigger example that would be really helpful for us. So let's take 1 comma 1 comma 1 comma 1 comma 2 comma 2 comma 4 comma 4 comma 4 comma 1 comma 3 comma 4 comma 6. And let's say that k is equal to 2. We need the two most frequent elements. So let's first store the frequency of each element. So 1 appears 1 2 3 4 5 times, so 1 comma 5 comma 1. 2 appears twice, 4 appears 3 times, then 4 appears 4 times, so this is going to be 4 comma 4. 3 appears only once, so 1 comma 3, and 6 again appears only once. Now let's try to go ahead and insert these elements into the heap, and now I'll only maintain the size of the heap as 2. I'll not insert extra elements or the elements which are not required. So obviously first 5 comma 1 is going to go into the heap, and then again 2 comma 2 is going to go into the heap. So because I need the two most frequent elements. Until now, obviously 5 comma 1 and 2 comma 2 are the two most frequent elements. I've just encountered two elements, so obviously both will go into the heap. So now we reach the third element, 4 comma 4, and we need to check that whether 4 comma 4 is going to go into the heap or not. So what is the logic of inserting 4 comma 4 in the heap? If the frequency of 4 is actually greater than the smallest frequency, whichever smallest frequency is present in the heap, then 4 comma 4 should go and that smallest frequency should come out. So if I have frequencies like 5, 2, 3 and 6 in the heap, and someone gives me an element which has a frequency 4, and I need the 4 most frequent elements, should this 4 go into this collection? Yes, obviously this 4 should go into the collection, but which element should it replace? It obviously needs to replace the smallest element of this collection. So if 4 is going to go into this collection, then obviously it is going to replace 2, so 2 is going to come out and 4 is going to go in. So we just understood that to insert a new element into the heap, we need to check that if the frequency of this element is actually greater than the lowest frequency present in the heap. If it is greater than the lowest frequency present in the heap, that element should actually replace the element. But now what we were doing is we were actually making a max heap. And in max heap, it is really easy to check the greatest element present in the collection. But what do we actually need? We need the smallest frequency in the collection, and we need to get that smallest frequency in most optimal way. And if we need to get the smallest frequency in the most optimal way, it actually makes sense to use a min heap instead of a max heap. So that's true. So in our third logic, we actually use a min heap instead of a max heap. So let's start from the starting. So if we make a min heap, then the first element which is going to come into the min heap is going to be 5 comma 1. Now second element 2 comma 2 gets inserted, but obviously 2 comma 2 is not at its correct position according to a min heap, so both these will get swapped. So we'll have a heap which will look something like this now. 5 comma 1. So now 4 comma 4 comes. It is really easy to get the smallest element of this collection. We can get it in O1 time, O of constant time, and we just need to check this. We just need to check this smallest frequency, and we just need to check the current frequency. If the current frequency is greater than the smallest frequency, then obviously this needs to be removed and this needs to be added to the heap. So first, obviously we'll remove 2 comma 2, so the remaining heap would be 5 comma 1, and then 4 comma 4 will be added to the heap. So if 4 comma 4 is added to the heap, obviously the node comes as the last node, but these will get swapped, so the heap will look something like this. Now I move to the next element, which is 1 comma 3. I compare it with the lowest frequency right now, which is 4, and 1 is not greater than 4, so we do not insert it. And then I come to my next element, 1 comma 6. Again, 1 is not greater than 4, we do not insert it. So this is the final heap, which is actually storing the two most frequent elements, and we can just extract both these elements from the heap and then return these elements. So let's try to analyze that what is actually the time complexity for this particular solution. So first, we obviously parse the entire array to create to get the frequency of each element and store that frequency. So that parse is going to take big O of n time. And next we are inserting each element into this heap of size k. So in the worst case, what will happen that every time the new element which I am getting needs to be inserted into the heap. So if that is the case, then n elements get inserted into a heap of size k, and each insertion takes log k time, and for each element this happens. So the complexity for that will be n big O of n log k, and then again I need to remove elements from this heap of size k. So the final step is going to take k log k time. So this is going to be the final time complexity of this particular solution. Now it makes sense to do a quick discussion on how this method is actually more optimal than the last method that we discussed. So the time complexity for our last method was actually big O of n plus big O of k log n. Now what were these components? So basically big O of n was the time complexity for creating a heap of size n, and then k log n was actually the time complexity of extracting k elements. Now you may say that the complexity for the previous solution looks more optimal, but that is not the case actually. So one thing first, people try to prove that the second solution is more optimal by saying that the time complexity for the first solution is actually not big O of n plus big O of k log n. So they say that the time complexity for creating a heap of size n is actually big O of n log n. And if you take that time complexity, then you can easily see that the first solution becomes less optimal. Now if you compare this complexity and this complexity, then this one is very much optimal. But according to me, that is not the right way to prove that this is much optimal, because according to me, that n log n is not the actual time complexity for creating a heap of size n. It is actually big O of n. This is a very crude upper bound on the complexity. So that's why I feel that both the solutions are almost equally optimal if I'm saying that n is comparable to k. But in your interviews, maybe you would like to give the second approach because it is the general consensus that it is a much more optimal approach. But according to me, that is not the case. The only way they are proving that the second approach is much more optimal is actually taking the time complexity of building a heap as n log n, which I think is not correct. So yeah, I thought I should bring up this point, and just in case some if someone points out or your interviewer points out that it is not actually n log n, then you're able to tell them that n log n is can be taken as the complexity, but it is a very loose upper bound, or it's not asymptotically tight. If we take the asymptotically tight complexity, which is big O of n, then in that case both the solutions are almost equal in time complexity if I'm considering that n is comparable to k. So let's quickly go through the code for our second solution. So obviously this is our main method that is going to be called, and we are given as input k. We have to return the k most frequent elements and the original array. So first what we do is that we store the frequency for each element. We parse this initial array or the original array and store the frequency for each element. So that is pretty simple. We are storing a map, and the map is basically element versus frequency. So once we have frequency for each element, we are parsing the map and adding these elements to our heap. So priority queue actually mimics a max heap in C++. So, but as we have discussed in our second approach, we will keep the size of this heap as k. We will not add all the elements, we will just add k elements to this heap. And one more thing, we discussed that we actually need a min heap for the solution and not a max heap, but the priority queue by default mimics a max heap. So when we need to use a min heap, there are two ways in C++. So there is a little syntax that you need to remember to convert this max heap into a min heap. So we have discussed that approach in the upcoming problems. The second more handy solution is that instead of storing the actual numbers, we store the negative of the numbers. So let's say we have numbers 3 comma 2 comma 1, and if I make a max heap using these three numbers, the max heap will look something like this. But instead of storing these numbers, if I start storing their negatives and then create a max heap, then the max heap would look something like this. Now if I use this max heap, if I extract elements from this max heap and then take a negative or use their absolute value, then I'll be actually getting a min heap. So if I extract or delete the element from this heap, I actually delete one, and if I get the max element, I'll get -1, and I need to use the absolute value of it for my logic. So instead of storing the numbers, I am actually storing the negative of those numbers. But this trick only works when all your numbers that you're going to store in the heap are actually positive. So this is a handy trick which can be used when all numbers are just positive and you don't actually have to remember the syntax for defining a min heap. And I've used this approach in this particular solution, but there's another better approach, which is actually you make a min heap and not use a max heap. So I have discussed that as well in the upcoming videos. So let's quickly discuss the solution further. So as we said that we'll be iterating the map and we'll be taking each element one by one. So the key in this map is actually the element itself, and the value is the frequency. So I get the frequency, I get the number. And if the size of the heap, as we discussed, is less than k, then we do not have to check anything and we add the pair. Because if the size is already less than k, then obviously the current is going to be part of the k most frequent elements. And as we discussed, we are actually storing the negative of the frequency so that we can actually use this max heap as a min heap. If the size of the heap is not less than k, if it is equal to k, it cannot go greater than k because we always maintain the size of the heap as k. So what I need to check is that if my current frequency is greater than the lowest frequency in my collection. If the it is greater than the lowest frequency, I will remove that lowest frequency and add my current frequency. So what I do is I get the lowest frequency of the collection. So actually now, since we were storing negatives, this max heap is mimicking a min heap. So when I am extracting from this max heap, I'm actually getting the lowest values. But as this heap was actually storing negatives, so we need to again do a negative to get the actual value. And if my current frequency is greater than the lowest frequency in the collection, I do a pop is basically extract, which removes the root. And then I do a push, or push is similar as insert, so I insert my current element. And once I am done, this heap of size k will be storing the k most frequent elements. So I just need to extract all elements from the heap and add it one by one to my answer array, and then I return that answer vector in the end.